So there's some gnarly problems in this video. We'll see how it goes. I want to start off by showing you again that making a mistake is okay, and a common mistake, and how to recognize it and what to do about it. We're going to start with 326, where you need to find the antiderivative of 1 over x squared. Again, maybe don't copy this down. I'm going to show you first with a mistake, a common mistake, and how to recognize it. Maybe you just finished 1.6.4 on integrals with logarithms and said, oh, the antiderivative of 1 over x is natural log. So maybe the antiderivative of this is just the natural log of x squared. So if you do this, the way to notice that this is not correct, to always check your answer. Right? If we take the derivative of this guy, we're going to get 1 over x squared times the derivative of the inside, which is just 2 over x. And these always need to match. So be very careful. Just because we learned a new fancy rule doesn't mean that we use it all the time. This problem right here is just the power rule. It belongs in this section because it's important to remember and be able to problem solve everything holistically. Not just be able to use logarithm formulas, but remember everything else we've done and say, wait, I don't need to use a log here. Watch out for that. This is just the power rule, like so. Negative 1 over x plus c. And that's my warning for this whole section. Next up, what else do we got? 331. Yeah. Integral of dx over x times the natural log of x times the natural log of the natural log of x. I like problems like this, but I know some students don't. So this looks like a mess. The inside function, and actually this I believe would work. Inside function's natural log of x. We let this be our u. Then when we take the derivative, we get 1 over x, which is good because we have a 1 over x. The problem with this, it's not really a problem, but we've talked about it before. This is a good choice of u substitution. It's just not the best choice. And in the u substitution section, I showed you that you can sometimes have to do 2 substitutions, a u substitution and then a w substitution. And that's what would happen here if you let this be your u, which is 100% okay. So what's the better choice? What if this is our u? Let's see what happens. If it's the natural log of the natural log of x, well then the derivative of that, the derivative of this outside ln is 1 over the inside. Chain rule says we have to multiply by the derivative of that inside, which is this, which gives us that du is 1 over x times ln of x times dx. Oh. And that's exactly what we have. Let's rewrite this integral before we go further though. This is 1 over the natural log of the natural log of x times 1 over x ln x dx. Now, it looks a lot different, but there's still only a dx on top, just like we wanted. And on the bottom, there's x ln x and ln of x. So this is a very helpful way to rewrite it, because now this is exactly our du, and this is just 1 over u. We get the integral of 1 over u du. What started out so messy is now so beautiful. Just like your house after a good day of cleaning. Or maybe you just always clean a little bit by little bit, and your house never gets to that point. It's an easier thing to do. I don't always do it, but it's true. Antiderivative of 1 over u is the natural log of the absolute value of u. And this is the really fun part, okay? Because look, what's u? So u is the natural log of the natural log of x. So when we plug it in, we have the natural log of the absolute value of the natural log of the natural log of x. Wow. What a fun problem. So do we need the absolute values here? Well, the domain of this problem in general is actually really finicky. The domain of natural log is x is positive, but that's going to give us some negative answers as well. So it has to actually be x is bigger than 1. And if x is bigger than 1, this guy could be positive or negative. Yeah, we do need the absolute values. What a fun one. Triple natural log. Function inside of a function inside of a function. That's a good one. Oh, I didn't mute my email. I just got an email. What kind of email did I get? Oh, I'm not going to check my email. Anyway, which problem is next? 343. Okay, so initially I was going to do 343, and I was a little nervous, and I was like, oh, I'm going to show my students what to do if you don't think it's going to work. Well, it doesn't work at all, and then I thought about it some more and realized it's a typo. I looked at the final answer in the back of the book. This guy up here really needs to be a 3 for this problem. So if you want to look at what I tried, you can, but really all that matters is that we do the actual problem. So this is a great choice for a u substitution because the derivative of the inside is very close to what's on the outside. We'll let u be x cubed, so du dx is 3x squared, or du is just 3x squared dx, which we almost have. We can get it if we multiply by 3 and divide by 3. That gives us 1/3 the integral. 3x squared dx is just our du, so everything in blue just becomes du, and this just becomes the natural log of u right here. And now we use the formula. Again, this is really only true for certain values of x, but now we use the formula in the book. That is right here. That the antiderivative of the natural log of something is that thing times the natural log of it minus 1. So it's going to be u times the natural log of u minus 1 like that. Again, there's still a 1/3 in front. The only reason the 1/3 doesn't get applied to this c is because a third of a constant is still a constant. This is our convention. This is what's usually done. You could just rename your c's over and over again. Now we get, this is just 1/3 times u, which is x cubed, times the natural log of u, which is x cubed, minus 1 plus c. And I would probably take this answer, but I'd be a little grumpy about it. Maybe give you a sad face because we can go a little further. Remember your properties of logarithms. This 3 can actually come out in front. This is 3 ln x minus 1 like so. And that makes things a lot nicer. You should be able to check your answer with the book, which is not what I got at all. Maybe I don't know what the book is doing. The book already has an impossible problem, and then their answer for the impossible problem is different. So I'm going to check my answer a different way. I'm going to check my answer the way I tell you to check your answer. I'm going to check it by taking the derivative. So we're going to have to use the product rule. The derivative of the first guy is just going to be x squared. Second guy stays by itself. And then the first guy times the derivative of the second, it's going to be 3 over x, like so. And we simplify this, and that's going to be 3x squared ln x minus x squared plus x squared Oh. Wait, I did make a mistake, right? Because the original problem wasn't 3x squared ln of x. Oh, it was! No. Oh, wait. Ah! All right, I'm having a crisis at the moment. Right? We can use the properties of natural logs again. An exponent can go inside, right? You can just go backwards. So this is the x squared ln of x cubed that we started with. And I should have, so again, this is a good sign, x squared ln of x cubed, that's what we wanted. But what I should have started with saying is that if we wanted to, we could move this 3 out. We didn't want to because of, we wanted to keep it inside so that the u sub would work. But yeah, that's interesting. I'm going to think some more about that later. I'm 99% sure that the book has a problem that's not possible, but either way, I want you to do my modified version of this problem, and then I'll think about it some more. Okay, next up, 353. Oh. Says, says do this. Antiderivative of the natural log of the cosecant of x times the cotangent of x. Now, it's telling us to do a substitution. Right off the bat, though, the natural choice for the substitution is cosecant. Derivative of cosecant is negative cosecant, cotangent. Doesn't seem super useful as it is. So let's use properties of logarithms. Remember, cosecant is 1 over sine. Cosecant is just the reciprocal function of sine. And cotangent is cosine of x over sine of x. I don't know if this is right, but it's something to try. Okay, so remember that inverse sine is not the same as sine of x to the negative 1, even though we write it kind of like that way. We can take this negative in front. This becomes negative natural log of sine of x times cosine of x over sine of x. And the question is this any better than what we started with? I'm asking that question for myself too. I see what's going on. So we didn't have to do this, but it was still potentially useful. Because now, what do I think I want to do? Well, what makes sense to me is letting u be sine of x. And now we have something similar, but I think it's a little easier to work with in this framework. Again, kind of showing you that you don't have to find the best answer right away. Is if the u is sine, this is our du right here, which is good. And then we're still going to have something like this over here. That's okay. Let's play with it. I want to show you what happens if you find something that works that's not perfect. I know what you were supposed to do now, but if it's not obvious, this is good practice. So if u is sine of x, what's our derivative? It's cosine. So du is just cosine of x dx. So this guy right here is our du. That negative can come out in front. We have the natural log of u times 1 over u du. So this still doesn't look amazing because we still have that multiplication. We're going to use another substitution. So this is another example of there was a substitution that we could have chosen that would have done it all at once. But if you didn't see that, I didn't see that. If you didn't see that, then you can just do 2 substitutions, one after another. Let's do a w substitution. Why am I choosing natural log of u? There is no inside function. Not really. But this choice is because what's the derivative of this? 1 over u. This is going to be our dw, which works out nicely. So the derivative of w with respect to u is 1 over u. So dw is 1 over u du. And that's nice because now this is our dw exactly. So we get negative antiderivative of, this is just w now, dw, just the power rule. Add an exponent, divide by the exponent, plus c. And then we plug in w, and then we plug in u. W is the natural log. This is shorthand that you can sometimes see, or sometimes you will see. It's just like trig shorthand. And then u was just sine. I actually will write it the other way. And we could check our answer. In fact, after this, the day I'm having, I do want to check our answer. If we take the derivative of this, we should get that original integrand. So the power rule, negative 1/2 times 2 inside stays the same. Subtract 1 and multiply by the derivative of the inside. Derivative of the natural log of sine of x is 1 over sine of x. Chain rule again, multiply by the derivative of that inside, which is cosine of x. So all in all, what happens is that we get the negative natural log of sine of x times cotangent of x. And then just like before, that negative can move in and turn that into a cosecant. Great. So not necessarily the way that the book wanted you to do this problem, but it is a way to get to the correct answer. And that brings us to the last problem, which is probably going to be a doozy. But I wanted to do it because I don't want to always just give you the worst problems and leave you hanging. So let's do 388 together. Again, haven't looked at this yet. Just scanned through it and said, yep, I want my students to do this problem. So the sine integral defined as s of x is, I'm going to write that down. S of x is the integral from 0 to x of sine of t over t dt. Is an important quantity in engineering. So anyone who's planning on going into engineering, I'm not an engineer myself, but I'm taking it on faith that this is something important that we can use and connect with calculus. That's why I put it in this class, because I know I do have quite a few engineering students on average. So although it does not have a simple closed formula, what that means is we can find a formula for the derivative of any function, but some integrals, there's not a formula like that. Okay, again, the very classic one of that is e to the negative x squared. Read about this if you want. It's related to the error function. If you want to Google that or ask me for links. Okay, so there's no simple closed formula for this important thing. There's no easy way to take the integral, even though it looks pretty simple. Sine of t over t doesn't look that bad, but it's not simple. Okay, so it's possible to estimate if x is large. And in fact, we have computers, we can estimate it kind of for any x. That, as a side note, by the way, should mention, this is also extra tricky, because if we look at this function that we're integrating, right? We can think about this as the area under this curve from 0 up until some x. And remember that this function, wait, does it not know that t is this function is not defined when t is equal to 0. You get 0 over 0. But we know the limit's 1. We got that from L'Hopital's rule. Okay? But anyway, even though the function is not defined at 0, there are still ways that we can do some interesting things, and area under this curve still makes sense. There's some cool stuff about that, but I'm not going to go into that here. Okay. Oh, distracting myself a little bit. All right, so we're going to estimate its behavior if x is big. Again, this is the function that we're looking at. And as x gets big, right, sine is oscillating. We could use the squeeze theorem to talk about this. Sine continues oscillating, but as t gets bigger and bigger, as we integrate further and further on here, well, we're dividing by a bigger number. And so it's oscillating, but it's oscillating closer and closer to 0. Okay, so show that for k bigger than 1, this is true. Do not get overwhelmed at this. We're trying to prove something. So we're going to assume k is bigger than or equal to 1. We're going to start with one of those sides, your choice, and try to get that thing is less than or equal to the other side, or greater than, depending on which side you choose. So we're just going to start with the left-hand side. A very common, if we're trying to prove something, we'll start with the thing that we think we can work with more and try to get it to the right-hand side. And we're not proving an equality anymore, we're proving an inequality. So sometimes we won't connect things with equal signs anymore. So we're just going to start with the thing on the left, use the hint. So we're going to say sine of t plus pi is negative sine of t. And let's just start with that left-hand side. We want that the absolute value of s of 2 pi k minus s of 2 pi times k plus 1 is less than or equal to 1 over k times 2k plus 1 times pi. We'll start with the left-hand side and prove that it's less than or equal to the right-hand side. As a side note, this is something that really pops up in Calc 3 as well with, I believe the term is telescoping series, when you have a plus and then a minus and then a plus and then a minus of things that are getting smaller and smaller. That's really what we have here. Because basically what we're talking about is that this integral, right? Because s, it can be thought of as an integral. So saying if we're integrating up to 2 pi k, and then we're integrating up to 2 pi the next k, this top part is 2 pi periodic, and the bottom is not periodic at all. So it's this whole function's not periodic. But eventually, this is basically going to be saying that the area in one of those periods, the difference between that area, no, it'll be talking about the area of that period from 2 pi k to 2 pi k plus 1. It's not a true period because this is not truly periodic. It's just kind of. It looks kind of periodic. It's like periodic, like with a scaling factor kind of a deal. That difference can be bounded by this. Another very common thing in math, physics, engineering is if we're trying to restrict some quantity or show that something's going to 0 or show that something converges and doesn't behave wildly. Converges is another word that we haven't introduced in this class. We're just going to try to find an upper bound for it. Say, I don't know what this is, but I know it's always smaller than something else. Again, something that we did with the squeeze theorem. Now, you don't need any of this context to do this problem. I'm just trying to show you why it's interesting and like how it ties to future things. So to do this problem, all you have to do is say, what's the left-hand side? And write it out. So that's not super easy, be careful. But you can do it. The absolute value of this function when x is 2 pi k. So all we're doing is taking this box and replacing x with 2 pi k. Nothing changes in the integrand. And then we're subtracting the next one. All we're doing is replacing x with 2 pi times k plus 1. And right off the bat, properties of integration is going to give us something nice. We're integrating area under the curve. Well, this integral is just this integral plus another one, right? And we have an absolute value, so we can switch the order, right? The difference between these, we can switch the order. Let's just copy it down real quick. We can switch the order of these because there's an absolute value, right? A minus B is the same as B minus A, except maybe it'll have a negative. And if you have an absolute value, that negative doesn't matter. So if we write it like this, just switch the pi, or the k and the k plus 1. It's still true because of this absolute value. Again, to really show what's happening here, the absolute value of the difference between two numbers doesn't matter. 5 minus 3, 3 minus 5, you take the absolute value, you'll still get 2. That's what's happening here. And now we use properties of integrals to combine these. This is just the single integral from 2 pi to 2 pi times k plus 1. How do we do that? Well, all we're saying is that if we have some function and we're finding the area up to one point and subtracting the area of an earlier point, what's red minus blue? Well, red minus blue is just green. That's exactly what we're doing here. Properties of definite integrals. Okay. So far, we've only done equality. Let's remind ourselves, maybe off to the side, we want this to be less than or equal to. Oh. We want this to be less than or equal to 1 over k times 2k plus 1 times pi. And so we simplified and combined the integrals, and that's great. But we can't evaluate this. And the book told us that it was not possible for us. It says it doesn't have a simple closed formula. So we're going to have to approximate this. All right, so this one, I had to play with this one a little bit because there's a lot of ways that you can get a bound for something. But we want to specifically find the bound that the book is asking for in this one. So do a couple steps. You get it to about this point when you combine the integral. Hi, October. And then that's when it really starts helping to visualize what's going on. What I did is, if you look at this region of integration, we have one full period of this function, which again, this function is it's not actually periodic, but you can think of it as in these little chunks up here, right? Where 2 pi is going to be one oscillate, like, the wave above and the wave below. And again, the magnitude of these waves is always decreasing as t is increasing, as t is getting bigger and bigger. This is just a note to remind myself of what we're trying to get at the end. So yeah, if we just think about this red and blue area, then really what we have is, the red area is going to be bigger than the blue area is negative. So what I decided to do next in this step right here is say, okay, well, let's split this up into red and blue. So this first one, I actually probably should have done it in the other order. But this is the blue area right here. Sorry, switch those. Right. This is the red area over here, the first part. And the other one is the blue area. And technically, this is going to be a negative value, so it's not really the area, but The blue net signed area is really what I'm going for here. And then I did essentially this first one stays the same. And then the second one, what I did is basically a U substitution. Is said that, okay, if we jump back a little bit, if we let U, where it's actually kind of the reverse of a U substitution, but it is a substitution, let T be equal to U plus pi. And if you do this change of variable, you can go from this guy on the left, that guy on the right. And I'll not go through the fine details on this. You can take care of this yourself, do this change of variable, and you can get everything with U's if you want, but they are equivalent. And then what happens is once we notice that, trying to remember what I did after that. Once we notice that, we can use the property that the book gave us, that this hint right here. Because we indeed do have the sign of t plus pi. So this sign of t plus pi just becomes negative sign, which changes this positive into a negative. And now this is very useful because we have now two integrals with the same region of integration. We can combine the integrands. And when we combine the integrands, I do it over here, we can get a common denominator. And in the process of getting a common denominator, it actually simplifies out really nicely to something like this. And so one of the reasons why I split this up, and again, now we're really only looking at this red area up here. One of the reasons why this is so nice is because now we know that on this portion of the domain, we used to have a full period, now we only have half a period. On this portion of the domain, we know sign is positive. Sign being positive is useful because now we, it's much easier to find a boundary or a maximum for something if we know whether it's always positive or always negative. If something's switching between positive and negative, the boundaries are a little squirrely, more squirrely. For example, if I say, if I tell you that x is less than 5, that doesn't tell you that x is small. Because x could be negative a billion. So it can still have a very large magnitude. So it's much easier to bound something if we know that something positive is small. And so that's kind of the rationale for why we wanted to go there. And it wasn't, that one took me a while. That's the step, dividing this into two regions. That step took me a while. And what eventually tipped me off to it was the actual hint that the book gave. So, okay, we have to use that hint. And that's what made it easier to get to this point. So I copied that onto the next page. This is the exact same thing as before. And then this was the other big trick for this problem. Again, we know sign is positive, so we have sign times this other guy. And what do we know about this other guy? This is basically a reciprocal squared function. It's kind of like a function transformation of this guy. And so that's going to be the biggest, because again, we're trying to find a bound, and we're trying to find something that we can integrate. So there's two ways of bounding this to try to find something to integrate. We can either try to bound the signs between -1 and 1, which is something that I also tried, or we can try to bound everything else. If we find a bound for everything else over here, well, it's going to be the biggest at the left-hand point of that interval. Why is it going to be biggest on the left? Because it's a decreasing function. As t gets bigger, the denominator gets bigger. As the denominator gets bigger, the whole thing gets smaller. So the biggest it's ever going to be is at this value of t. And so if this is always smaller than this, we can multiply both sides by sine of t, which is positive here. If we didn't know whether sine was negative or not, we wouldn't be able to keep this inequality. If sine was negative, you multiply both sides of an inequality by a negative number, you have to flip the inequality. So that's why that's useful. And so now once we have that bound, I always want to say bind. Once we have that bound, well, we can just replace this with the less than or equal sign and replace this with what is on its right-hand side. And then I simultaneously, so that's where this comes from, factoring out all the constants. I simultaneously said, well, as soon as this integrand has nothing to do with, as soon as this integrand is perfectly periodic, you didn't have to do this. But now that we're actually integrating a periodic function, we can just say, well, all the periods are the same. So instead of looking at this half of a period, let's look at this half of a period, because we know sine's going to be the same for on the first half of any of its periods. 0 to pi is going to be the same as 2 pi to 3 pi, going to say same as 4 pi to 5 pi, and so on. Just makes it a little easier. You didn't have to have this. You could keep the old limits of integration right here. And now that's the hard part. And now it's just evaluating. So, okay, you know, cancel the pi's, evaluate the antiderivative, use what we know about trig, and simplify your final answer. Okay, one other step that was a little tricky, again, going from here, these green guys, to what's afterwards, I just factored out a pi out of the right. If I factored out a pi out of the right, we're left with 2k plus 1 on the inside. That's really what was going on between that step and that step. So pretty messy problem. And again, one of the trickiest parts of this problem is there are so many things that we could have proven. There are so many bounds we could have made. But trying to find the logic and the algebra to get to the bound that the book wants was a little trickier, at least for me. But I wanted to actually give you an example of one of these messier problems instead of just saying, well, good luck. Because these are really the sorts of problems that challenge you and can build good habits and problem-solving techniques that, again, are you going to need this during this class? No, probably not. But will this help your ability to do math and solve problems in future classes or future careers? Absolutely. Okay, so science classes, math classes, that's the reason why these are going in the homework. Again, like probably a fair amount of engineering students or people who are interested in engineering in this class as well, gives it an extra benefit to problems like this. Hope you enjoyed it. Let me know if you have questions. I like answering them. I like working on problems that are hard. And yeah, this is really also something that, well, that's a rant for another time, but have a great one, and bye-bye.